Should have worked on 6.4 and 6.5. Or the last things that we talked about. Do you guys have any questions from homeworks? Or questions in general? Yeah, Rita.
Did you remember
from which section?
Oh, 6.4.
6.4. Wow. I forgot to open my thingamajigger. There you are. 6.4, number 21. This one, yes. Okay. A tank is full of water. Find the work required to pump out of the spout. It says to use the fact that water weighs 62.5 pounds for, only for 23 and 24 because they give you it in feet. Okay. All right. So let's see here. So I know that the mass of water is going to equal the density times the volume, right? And I know that force then is mass times distance. Or acceleration. Oh, yeah, okay, so I'm sorry. Work is force times distance, yeah. Yep. Okay. Thank you. So first thing I want to do is try to isolate the mass because I know that's what's going to go in there. So the volume for this water, like when the water's at a given height, when I take the cross section, it's going to be like a rectangle. And that rectangle is going to have different width, but identical length, right? It's always going to be 8 meters long, but the width is going to change based on the height of the water, right? So I'm going to start there. So I know the volume of this figure is going to be area of the base times the height because it's a rectangular prism. The bases here are going to be these triangles, right? And the height there is the 8. So that triangle, we're told, has height 3 and base 3. Hello. So, oops, where did my thing go? There it goes. So my volume formula is going to be like the base of the triangle times the height of the triangle times the height of the prism. Now that height of the prism is constant. That's always 8. but I want to somehow relate the base of this triangle, or the width of the rectangle here, even in that case, to the height of the triangle, since the height is the thing that's going to be what we need for the work, right? So I want to rewrite this so that that width is in terms of heights. So I'm just going to like sketch a quick picture here. So I can say that like base of the triangle over height of the triangle is equal to 3 over 3, or just that those are the same. Oops. Let's write it this way. It's okay there. Okay. So the force in terms of, I'm just going to call that X. Is going to be 4. Actually, I'm not sure I want to do that yet. Let me think about it for a second. So my force in terms of h of t is 4h of t squared times 9.8, because the acceleration is just due to gravity. And my work then is going to be the integral going from let's see, the lower bound should be 5, right? So we have to pump it up 5 meters from the very bottom. And the upper bound should be 2, right? Because at the very top of the thing, we still have to pump it up 2 meters. Okay. But that height there is not the same as the height of the triangle, right? Because the height of the triangle is never going to include, right? Like the height of the triangle at some point needs to be 0, and the height of the triangle at some point at most could be 3. So we're going to have to do a little bit of variable adjustment there. Jacob, what's up?
So when you do the force equation, how come for the mass you don't use volume?
Oh yeah, I forgot to do the density there, right? Yep. Sorry about that. Yeah, put that 1,000 in there too. Yep, thank you. All right, so let's think here for a moment. So what we're really doing here, taking that guy and pumping it up, it's going to be like 3 minus the height of the triangle. Make sure I get this right. Stop being stubborn and just look it up. You don't remember. It's embarrassing. All right. This is 21. Okay. All right. Okay. Let's rethink this then. I made a bad assumption here at the beginning, Rita. So I'm just gonna do this for a minute. So the stuff that we're actually pumping is this rectangle, right? Oops. So the volume of that rectangle is really just width times 4 times like delta x. Or sorry, width times 8 times delta x. Right? Because we're just pumping a little rectangle worth of water that's delta x, like deep. You're thinking about it as like a box that's like delta x deep, like, or tall, or whatever you want to. And I know that just like we did here, that width is the same thing as the height of our triangle, right? So I'm just going to call like, yeah, still from this. So x is going to be the height of our triangle. So our mass then, or I'm sorry, I should say our force then is 8x delta x times 9.8 times 1,000. And the work then that we need to do is going to be, that force, and then the distance it's going to be traveling, come on now, is going to be five minus x. Is that because it's total distance of 5, and then wherever the height of the triangle is, you know, like we're not pumping that because we're just pumping from the surface of it. So we're going to have, let's move all this stuff out front. And then we just have to think about the bounds of integration now, right? So x here is representing the height of the triangle, or the depth of the water, whatever you want to think about it. So we're just going from 0 to 3. And that should do it. Jacob.
If x is representing the depth of the water, what represents like the width of the rectangle?
Well, the height. That's embarrassing.
Sorry.
The height of the water and the width of the rectangle are the same.
Oh, okay.
Remember, that's what this similar triangles argument we did right here was.
Okay.
So that x is the width is also the height of the triangle, which we're going to call x.
Okay.
Is that? Yeah. This is like a hard example. This was hard. Like if it felt hard, that's normal. This was hard.
These ones.
Isabel? Hopefully better than I just did this one. Yeah, I think this one should be easier since it's the aquarium is a rectangular prism, so like the cross sections are the same at all heights. Okay. So when we look at any kind of cross section here, that shape is still a rectangle, right? So the volume of that rectangle is going to be length times width times height. Where x is going to represent that height of the water. So our force then is our volume times our density times gravity. And then our work should be integrating x, which is the height of our water. Oh, I should put all that stuff out front, huh? Put all those constants away, Mr. Kulik. And then the height of the water, if I want it half the water out, should go from 0 to half of the total height. So when we pump 0 distance, that's where the water's all the way at the top. Pump half a meter's where we're at half the water's out. And that ought to do it for us, Isabel. Does that feel okay? Again, what makes this one so much easier than the previous one is that that cross-sectional area at every height is constant. Which, boy howdy, that made it a little bit easier, right? Giselle. 23. Yeah. All right. So here we have same idea. We have some tank of water and we're trying to pump it out through the spout. Notice the spout is here at the height of the figure. So at any cross section, we have a circle, right? Okay. So what I'm going to do is I want to do like a similar figures thing with that piece. I'm going to redraw that though. So I know that's 6, I know that's 3, that's my RC. I'm going to call this distance X, so like that's the distance the water is going to have to get pumped up, because remember RC is the height of our water, or is the radius of the water at the pumping height, right? So if this the whole thing is 8, this section down here should be x minus, or 8 minus x. Because I know the whole thing is 8, right? And if I think about this, actually move that 6 for a second. If I do like one of these guys up here, that piece has to be 3. And because the whole thing is 6, I know that piece has to be 3. So I also know that this piece has to be 3. So I'm going to call that little thing D. And I'll make a similar triangles argument to figure out kind of what D is. So I can say that D over 3 is equal to 8 minus x, that's the height, over 8. So if I cross multiply, I get D is going to be 3/8 of 8 minus x. So RC then is 3 plus 3/8 8 minus x. So far, so good, Giselle? Okay. So I know my volume is that area times delta x. So that's going to be pi. And then my radius that I just figured out, squared delta x. So my force is going to be this thing, and I surely could simplify that down. I'm just not super duper interested in, because eventually I'm just going to want to type this in my calculator, right? Like, oh, Rita, go ahead. Oh yeah, it should be. Thank you. Yeah. Because this is in feet, right? So what did they tell us? 62.5. Thank you. And then 9.8 needs to be different because it's in feet. That's 32. So units match, right? Giselle, you good with that? So those guys are different because the measurement is in feet. Alternatively, I could have converted all the feet to meters and then stuck with the old ones. But like, oh well. All right. So we have our force equation. So let's see here. Our work is this is our x, right? That's the distance we're pumping. Because that's like this distance here. So the work should be the integral of x times, actually, let's be smart about it, Kulik. Let's take all those stupid constants and write them in the front. Okay. So this x is the distance for the work equation. And then I just need to figure out the bounds of my integral. Well, when the water's full, it's pumping 0 distance because the spigot's right at the top. And when the thing is empty, we got to pump 8 feet because the water's at the bottom and it's 8 feet tall. So we'll go 0 to 8. And I think that ought to do her for calculator time. Yes, sir.
We want the change in x to the force form.
Right, that's what this x is.
Oh,
That's the
okay.
distance.
Okay.
Yeah. So again, work is force times distance. And that distance is just the x, right? So when I renamed my variables, when I drew that like similar figures picture, I was trying to be careful to call x the distance that the water has to go. Does that feel okay?
So change in x is the x,
Uh,
or is it the dx?
the change in x is the dx. This x is the distance from the force equation. Maybe I misunderstood what Jacob was asking. I thought I had the right answer for that.
No, I think you're right.
Okay. Yeah. Yes. Where did what? So I was making a similar triangles argument here. So like I have this triangle, and then I have like this triangle. So I said like d over 3 is equal to 8, which is this height, over 8 minus x, which is that height. Does that feel okay?
Yeah.
It was just tough to get to the similar triangles piece. Like that was a tough piece of geometry to go, oh, and then I draw this little dashy guy in here and like,
Yes.
yeah, yuck. If it was a full cone, it would have made it life a lot easier. Instead of whatever they call it, the frustrum. Sounds like frustrating to me. Okay. Last chance on these questions for today. We can always come back and do some more. So today we're going to talk about a new integration rule that we can use. This rule is called integration by parts. And this is like the integral equivalent for the product rule. So if you have the product of two functions that you cannot do a u sub on, the next step would be to try this integration by parts technique. So remember we have the product rule, right? So if I take the derivative of f of x times g of x, I get f times the derivative of g plus g times the derivative of f. Everybody's cool? If I integrate both sides, I know that the integral cancels out the derivative. So I just have f of x times g of x. And then I have the integral of the right-hand side. Everybody's okay there? Integrals distribute. And so if I subtract this piece from both sides, I have that this is equal to, like this guy minus that guy. So I have an integration formula for the product of two functions, provided that I can get the two functions to kind of fit right. Typically, when we write the rule for integration by parts, we say the integral of u dv is equal to uv minus the integral of v du. This is kind of the classical presentation of this. So we have a little bit of a choice to make when we go to apply this integration by parts formula. We need to pick which function is the u and which one to be the dv. Generally, the way we choose is we want to pick u so that when we take the derivative of u, we get a simpler function. We want to pick the dv so that when we go to integrate, that's an easy integral to do. From here on out, we're just going to do examples now. This is the whole idea. So we need to pick a u and we need to pick a dv. So my two functions are x and sine x in this example. Which one gets simpler when we take the integral of it? Or, sorry, take the derivative of it? X. So let's pick u to be x, and that makes sine x our dv. So far, so good. Okay. So we're going to say then that x, or the integral of x sine x dx, is going to be, well, actually, let's do this before we do that. So I need du dx, also called u prime, or we'll just call it du, to be 1, right? Or actually, I should say, okay, let's back up here a little. So 1, or that du is equal to 1 dx. And then v is going to be the integral of sine x dx. I guess I should put the dx here with that, sine x. And what's the integral of sine? Close, negative cosine. Okay. So my formula says u times v minus the integral of v du. So that's going to be u is x, v is negative cosine x, and then we have the integral of v, which is negative cosine x, and du, which is just dx. So what's the integral of cosine dx? Sine. Notice that I made it plus. I took the negative out to make it a plus, right? Catch that? Can you check this? Yeah, all we have to do is take the derivative of what we just wrote and make sure it gives us what we started with, right? Let's do that real quick. So we would have a product rule to do the derivative of negative x cosine x, right? And what do you notice happens? And that's exactly what we started with, x sine x. Does that feel okay? I just took the derivative of that stuff in green.
Oh.
So I did a product rule on the x cosine x piece, and then just a regular old derivative for sine x. Yes. Shall we do another? Yeah, probably, right? Okay. So again, we need a u, we need a dv. Notice we have no antiderivative rule for the natural log of x, right? Everybody agree? That's not something we have a rule to cover. So this has to be done some other way. Could I u sub on this? Nope. Because the only thing you'd pick for u is the natural log of x, and if you could do, you know, like if you could do the natural the integral of natural log of x, you wouldn't need to, anyways. So I have two things here, right? I have natural log x and I have dx. Which one has to be the u? Natural log x, because I can't do the derivative of dx, right? What the heck does that mean? I don't know. That means that dv is just going to be dx. So what's v have to be? One. One. No. It's x, right? Think about it this way. If dv over dx is equal to 1, and you do this, right? Or if we think about it as the integral of 1 is, or I should, the integral of 1 dv is v. The integral of 1 dx is x, right? Go ahead, Rita.
I like the step we're on.
Mhm.
It's like, are you like finding like the like, I don't know.
Yes, to find v, I'm doing the integral of dv.
Oh, and then you found the dx.
So I said I let dv equal dx. When I did the integral to both sides, I get v is equal to x. Jacob.
And then when you do like integral, like sine x dx,
Mhm.
it just becomes like negative cosine x. Because if you did the integral of the dx, would it be x then?
So what I'm doing is the integral of 1,
Okay.
and that's x if
Oh.
if I have a dx there, and it's v if I had a dv there, right? I'm integrating the 1.
Oh. Okay.
Does that?
Yeah.
So the dx or dv or whatever is part of the integral symbol, right? It's telling us what variable we're integrating with respect to.
Okay, that makes more sense.
Sorry if I did a poor job of clarifying that point. Okay. So now the formula says I have u times v minus the integral of v du. What do we notice is happening here? Well, it's the integral of 1, which is x. So we can say x, natural log x, minus x, plus c. Let's do another. Is the pace okay? Am I going too fast? It's all right. All right. The next one, t squared e to the t dt. My u we should pick as, good, I would pick t squared. And the dv then is e to the t dt, right? Why wouldn't I want to do the reverse? Isn't the derivative of e to the t really easy? But if I compared the integral of t squared and e to the t, which one is easier? E to the t is the easier integral, right? Because what's the integral of e to the t? E to the t, right? That's so like easier integral than the derivative, or than the t squared, because t squared is getting to be a bigger polynomial when we integrate it. Everybody's okay there? So du dt is 2t. So du is 2t dt. The integral of dv and the integral of e to the t dt. The integral of dv is just v, and the integral of e to the t dt is e to the t. So far so good. So I have u times v minus the integral of v du. Oh my gosh. All right. What do you notice, though? Do you know how to do that? U sub's not going to work. Guess what we're going to do? We're going to do integration by parts again on that piece. So the u here will make t, and the dv will once again be e to the t dt. So hopefully you can see that du is just going to be dt, and v is just going to be e to the t. God bless you. if we recopy what we have, so we're going to have uv minus the integral of v du and that is just going to be e to the t.
Cool.
Oh, I dropped a 2 somewhere. Yeah. There's supposed to be a 2 there. That sounds right. Okay. All right. That go okay for us? All right, hold on to your shorts on this one. What should I pick as u? E to the x or sine x? Do either of them get simpler when we take the derivative? No, not really, right? Well, e to the x is easier to integrate, sure. I think, though, you probably want to go the opposite route. And I don't have a... it might not matter, actually, but I think I probably would have gone this route. But I don't know that it would have been super clear. This one might have been like, have to do a little bit of guess and check on. Oops, I should put the dx there. And the integral of sine x is negative cosine x. So I have u times v minus the integral of v du. Oops, it's not du. This is du. This v wasn't pointy enough for me. Okay. Now look here. Look what I have. Did that get any easier? No, but at least it's not any harder either. Right? So maybe we try this again. And let's just do that. Everybody who's so far so good? And then I have uv minus the integral of v du. I'm going to pause here and let you look at this and see if anybody sees it.
The same as the original one.
It's the exact same.
But that's good news. That's good news. Because what can we do now?
Add it.
Mm-hmm. And then we just divide both sides by 2. Tack a plus c on at the end, and we're done. Super tricky, right? That's as tricky as you'll see. And I wouldn't ask you something that tricky on a test. I don't even think if you're a BC student, you'd see something that tricky on the AP exam. It's not that bad if you've seen it before.
True.
If you haven't seen it before and you don't think, like, who goes, add it back over and we got 2 times the integral, and just divide by 2 and I'm done, right?
I would have never done it. 5 by 2.
Yeah,
I
that's.
saw the adding over, I just didn't think.
No, I would
5 by
never
2.
have.
And then be like, oh, and then I'm done,
Yeah.
right? Like, just put the plus c on at the end and I'm done.
Add over integral.
All right. So we've done some indefinite integrals with integration by parts. What about a definite integral? What difference does that make? Not really, right? What our theorem is, or what our definition here is saying is when I do my integration by parts, the u dv, or I'm sorry, the uv part, I evaluate at the bounds, and then the bounds just stay with me on the other integral. So I'm going to evaluate the uv part with the bounds, and then I still have to do the integral for the other piece with the same bounds. Let's do this as a
The VB doesn't get used in like answer, does it? It's just UV and the integral of VU.
v du. Yeah, we need the dv to get the v though
Right.
from the start, but yes, it's not part of the formula. Right, we have, g of x is our v. G prime is our dv. So, all right. So again, we don't have a antiderivative formula for tan inverse. We know the derivative of tan inverse is 1 over 1 plus x squared. But what's the integral of tan inverse? We don't know. We don't have a formula for that. So, integration by parts looks like our plan. Hopefully here it's pretty obvious our u should be tan inverse because, well, I can't do the derivative of dx. That has to be our dv. So du is going to equal 1 over 1 plus x squared dx. And then v is just x. Everybody's good? I skipped some of the work there, but it's like work we've done before, so I felt like it was okay to do that, to just kind of skate through a little bit. Okay, so our integral from 0 to 1, tan inverse of x dx is u times v evaluated from 0 to 1 minus the integral from 0 to 1 of v du. So far, so good. Okay. So tan inverse, well, we have tan inverse of 1 times 1 minus tan inverse of 0 times 0. So that just becomes pi over 4 times 1 minus 0. Then how are we going to do this piece? Yeah, good job, Isabel. This is just going to be a u sub. What should u be? 1 plus x squared. So du dx is just 2x. So du over 2 is just going to be x dx. And let's go ahead and do so we don't have to sub anything back in. So I'll change the bounds. And I have 1 over u times 1 over 2 du. So that's just going to be the natural log of u, well, 1/2 natural log of u from 1 to 2. So pi over 4 minus 1/2 natural log of 2 minus natural log of 1. And what's the natural log of 1? 0. So I'm left with pi over 4 minus 1/2 natural log of 2. Is that okay? Yeah. Oh, well, it's either that or I have to plug the x's back in and keep the bounds. So doing either is fine. I usually like to switch the bounds, particularly when I have like logs and stuff involved. It just tends to make life easier to just leave the u there and just put a number in rather than having to like put an x in and then put the number back in also. But it's like 6 and 1/2 dozen of the other. It's purely preference. All right. I don't think I want to do that because look at all the space I left for it. And I'm not going to ask you to do something like that. All right. So for your homework, I just want you to work on 3 through 17 odds from 7.1. They're all just like do this definite or indefinite integral. So they're just all integration by parts problems. Just straight practice. There's no application, no theory, nothing funny going on. Jacob? Yeah, go for it. Let's get off topic.
When will we get our test back to look at?
I have to double check, but I think everybody's taken them, so I could do that possibly right now. I just have to double check to make sure everybody's. Oh, no, I know one person hasn't. Never mind.
Is it that?
Yeah, I think so. That's the one I would be worried about.
Figures.
No, but they're like the same tests, or close enough to it to where like if you handed him your test, it would make his test way easier.
What if we did it and then give them back again?
Yeah, I don't care about that kind of stuff. It's not like it's secret. Yeah, 1 second though. Okay, yeah, go ahead. You have another question?
No, I was gonna
Oh.
ask you.
Okay, yeah, let me do like, what do we have left? We have like 15 minutes? Okay, let me do like one little quickie thing, and then we'll, actually, who cares? Let's just be done. That's
Oh my
fine.
god. I was like, no.
That's fine. That's fine.